What if one of the biggest puzzles in physics, gravity, could be understood not with some brand new discovery, but just by looking at something we already know in a totally new way? That's the fascinating idea at the heart of a research paper we're diving into today. And it all kicks off with one simple but really profound question.
So the paper asks, what if gravity isn't just connected to escape velocity? What if it's actually defined by it? It's a pretty wild thought, right? That the speed you need to actually break free from a planet's pull is the key to understanding the pull itself. To really get why that's such a game changer, we need to take a quick look at how we've thought about gravity up until now. To appreciate just how different this new idea is, we have to start with the giants. I mean, we're talking about a concept that's been shaped by some of the greatest minds in the history of physics. Yeah, our understanding has evolved a lot. First, you had Newton, way back in 1687, who saw gravity as this straightforward force pulling two things together. Then, in 1915, Einstein just completely flipped the script. He showed us it's actually the fabric of space-time itself, getting warped and curved by massive objects. But here's the thing physicists are still stuck on today. Gravity just doesn't like to play nice with the other fundamental forces. Trying to unify them all, to create a grand unified theory, well, that's kind of the holy grail of modern physics. And that's the massive puzzle this new paper is trying to look at.
And this is where our source material comes in. See, instead of trying to cram gravity into the boxes we've already built, it suggests we look at it through a completely different lens. It's proposing this new relationship, this link between a body's mass, its radius, and its escape velocity. To help us get our heads around this pretty abstract idea, the author uses this brilliant and honestly really simple analogy. It starts with something you'd probably find in a high school science lab, a magnetic stirrer in a beaker of liquid. Okay, so picture this. The beaker is the universe. The liquid inside it, that's space itself. Now, that little spinning magnetic bar, that's a huge object, like a planet. And the vortex, the whirlpool it creates in the liquid, well, that is its gravitational field. This analogy just perfectly shows the idea. The pull is super strong and orderly right next to the planet, but it gets weaker and more chaotic the farther you get. It's a really powerful way to picture gravity, not as some invisible force, but as a real physical disturbance in space. So, at the very heart of this entire theory is this one concept, escape velocity. It's pretty simple, really. It's the speed a rocket needs to hit to finally break free from Earth's gravity and just keep going into space. For us here on Earth, that magic number is about 11.2 kilometers per second. And what this paper argues is that this very specific number holds a much, much deeper secret. So how exactly does escape velocity become the key to everything? Well, the breakthrough in this paper isn't some crazy complicated new math. It's actually a really simple, almost elegant rearrangement of a formula that physicists have been using for hundreds of years. All right, here's the core idea. Let's break it down. Step 1. We start with the standard, totally accepted formula for escape velocity. You can see how it connects escape velocity, that's v, to the gravitational constant, g, the planet's mass, m, and its radius, r. Okay, step 2. Now here comes the twist. Instead of using the formula to find the escape velocity, the paper flips it on its head and solves for g, the gravitational constant. After a little bit of algebra, you get to step 3. And this is radical. The universal constant g is now being defined entirely by properties that are unique to a single planet, its own escape velocity, its radius, and its mass. Of course, a new equation is just a cool idea until you actually test it. So that's what the author did. They took this rearranged formula and applied it to the planets right here in our own solar system, using publicly available NASA data for their escape velocity, mass, and radius. And the results, well, they're pretty stunning. Just look at this table. Check out that last column for the calculated g. I mean, even when you're comparing tiny little Pluto with an escape velocity of just 1.2 kilometers per second to the absolute monster that is Jupiter at nearly 60, their calculated values for g are almost identical. They all hover right around that 6.5 or 6.6 mark. That consistency is the core evidence for this entire theory. So when the author averaged the results from all the planets, they landed on this value for the gravitational constant. The really crucial takeaway here isn't just the number itself, but how it was found. It wasn't based on some universal assumption. It was built from the ground up, using the specific, measurable properties of individual worlds. Now, with this new way to actually define g, The author takes it one massive step further. Because if you can define g using escape velocity, well, then you can redefine the entire equation for gravitational force itself.
Okay, check this out. On the left, you've got Newton's classic law of gravitation, with that big universal G right in the middle. But on the right is the new proposed formula. And look closely. By plugging in the new definition for G, the constant just disappears. It's gone. The gravitational force can now be calculated without a universal constant. All you need is the bigger object's escape velocity and radius, and the smaller object's mass. The universal force suddenly becomes a local property. So, what are the big takeaways from all this? First, this profound idea that an object's gravity is basically just a direct expression of its escape velocity. Second, it gives us a brand new method for calculating the gravitational constant g. And, maybe most importantly, it offers a whole new way of seeing the universe, not as a bunch of objects just floating around, ruled by some mysterious constant, but as this intricate web of interconnected bodies where each one defines its own gravitational influence. As the author puts it, this new perspective could let us better understand the individual relationships between all these celestial bodies. It completely reframes gravity. It's not just some universal background noise, it's a specific, calculable property that emerges directly from each and every object. This whole explainer, all based on one single paper, is just a powerful reminder, isn't it, that sometimes the biggest breakthroughs don't come from finding something new, but from looking at something ancient in a completely different way. And it leaves us with this one last fascinating question. What other cosmic laws are just out there, hiding in plain sight, waiting for a fresh perspective?